Dear students, we can discuss problem number 2 on beams. So here I can consider a problem on beam subjected to a uniformly distributed load. Uniformly distributed load is applied on a beam. So consider figure shows a simply supported beam subjected to a uniformly distributed load. Obtained the maximum deflection. Take Young's modulus E equal to 200 GPa and moment of inertia as 2 into 10 to the power 6 mm raised to 4. Here this is also beam only, but it is subjected to uniformly distributed load. So here the length of the beam is given 1 meter and they have not bifurcated into two elements. You have to consider a single element of the beam and determine the maximum deflection, right? So what is the difference between point load and uniformly distributed load? You know it well. Okay, so this UDL has to be converted into single load so that you can solve this problem easily. So first step, as I told in the previous problem, Young's modulus you have to convert into SI unit, kilonewton meters per meter square, and I calculate EI. You will get it as 4 into 10 to the power 2 kilonewton meter square. Here the steps are same. Only thing you have to convert the UDL into uniformly distributed point load. So to convert that, there is a formula that I can tell you while constructing the force vector. Okay, the first steps are same. Draw the FE model. Here only one element you have to consider here. You have to consider one element. Okay, then you have to represent the displacements and angular displacements both same. K you have to write EI by LE cube. That stiffness matrix you have to write, it is already told. Then calculate 6LE, 4LE square and 2LE square. The values you can substitute back in the stiffness matrix. So here only one element is there. You have to find out only one stiffness matrix. That itself becomes global stiffness matrix. This is a global stiffness matrix because only one element is there. Hence displacement vector you can write v1 theta 1 v2 theta 2 because only two nodes are there. Clear? So v1 indicates the deflection at node 1, theta 1 indicates the angular deflection or slope, we can call it as at node 1, not at node 2. Similarly v2 deflection at node 2, theta 2 the slope at node 2, like that it is. Then force vector as usually force moment. For first node force and moment, for second node force and moment transpose. So here if you have UDL in the problem, there is a formula directly considering that UDL to construct a force vector. What is that? You see here, F global load vector is equal to P minus PL by 2 minus PL square by 12 minus PL by 2 plus PL square by 12. This is fixed for any one element, having two nodes. So 1 and 2 nodes are there. So here for this beam element, the force vector is this one, where P is the UDL. Okay, P is UDL. See here, PL how to calculate? 12 is there, no? P, UDL 12 as I given in the problem, as I said already. 12 into 1, length of the element is 1 meter, 12 into 1, so 12 kilo. Similarly, PL square, 12 into 1 square, so that is also 12 kilo. So I substitute here PL value 12, PL square is also 12, means this is also 12 and 12. minus sign that depends upon the rotation. So if the load is applied here, how it rotates, how it bends clockwise and anti-clockwise depending upon the sign is constructed. But for any beam element subjected to vertically downward loads, this is a standard minus, minus, minus and plus. So only the last movement becomes in the reverse direction of the previous three, hence you have to remember this. So after substituting and calculating, you will get this force vector. The next step, again it is same. What is that? Equilibrium equation KQ equal to F, and after solving and substituting the boundary conditions, what are the boundary conditions? You know, V1 theta 1 and V2 are 0. Why? Because first node is fixed, second node is again it is roller supported, V2 is 0 and theta 2 will be there. So you are supposed to calculate theta 2. So substituting back in the equation and solving, you will get the value of theta 2 as 6.2 pi into 10 to the power minus 4 radians. Our aim is to find out the maximum deflection, not the deflection at node 2, where the maximum deflection happens. To find the maximum deflection of the so that occurs usually at node middle of the span. You know, it is subjected to UDL. Maximum deflection happens at the middle of the node. So we know that V equal to H into Q. So this is a well derived formula. V is equal to H into Q, Hermite shape function. Q is the displacement vector, and V that is also deflection. Okay, so V equal to H1 V1 plus so and so. This is also already derived and said in the previous video, where H1, H2, H3, H4 are the Hermite shape functions. So you know the value of zeta. From the boundary conditions, you know the values of V1, theta 1, V2 are 0. Put them in the above equation here, right? So substituting, we get V max is equal to LE by 2 H4 theta 2. That is equal to, so if you substitute V1, this factor becomes 0. Substitute theta 1 0, this is 0. V2, if you substitute 0, where it is V2. So V2 means this one only, this will becomes 0. So actually this is V2. V2 it is. Okay. So this V2 becomes 0 means this factor, only this factor exists. So that is here. LE by 2 H4 into theta 2. LE by 2. What is the value of H4? That is minus 1 minus theta plus theta square plus theta cube by 4. This is also derived. Hermite shape function video is there. You see that it is derived one. So I substitute here directly the value of Hermite shape function. So next, substitute the value of theta 2 as you determined already. Then you will get the value of V max as 7.8 into 7.812 pi into 10 to the power minus 5 meter. So this is called as the maximum deflection. It happens at the middle of the beam. Thank you. Practice such problems. If you have any doubts, you can ask me or you can call me.